Welcome. There is nothing to do right now but rest. Let your shoulders sink into whatever is holding you, and let your breath slow on its own. Tonight, we drift through something enormous and unhurried, whether the universe, in the end, forgets. Human memories begin to fade within hours without reinforcement. A face, a conversation, a scent, within a single afternoon, the details start to soften. The hippocampus holds a memory loosely at first, like wet clay before it hardens. Without repetition, most of that clay simply settles back into formlessness. Your brain rewrites a memory every single time you recall it. Neuroscience calls this reconsolidation, and it means no memory stays untouched. Each time you revisit an old afternoon, you are not replaying a recording, you are quietly reshaping it. The version you remember tonight is already a little different from the one you had last year. Passed from voice to voice, oral traditions can preserve stories accurately for only a few generations. A grandmother's tale reaches her grandchildren mostly intact, but by the fourth or fifth retelling, names blur and details drift. Anthropologists studying oral cultures find the same pattern nearly everywhere. The story survives, but the exact shape of it does not. 5,000 years ago, written language finally emerged. For the vast stretch of time before that, human thought left almost nothing behind but bone and stone. Writing let a sentence outlive its speaker for the first time in history. It was a small, quiet invention that changed how long a thought could survive. Most personal photographs from the 19th century have no identified subjects today. Boxes of tintypes and daguerreotypes sit in archives full of faces no one can name. The paperbacks once held handwriting, but ink fades and paper crumbles faster than memory would like. Somewhere, a great-great-grandmother still looks out from a photograph, nameless. Digital photographs become unreadable within decades without migration. File formats quietly go extinct, drives fail, and the software that once opened them disappears. A picture taken with great care can vanish not through fire or flood, but through simple neglect of an old format. Preservation, it turns out, needs constant tending. 100 days is roughly how long the average website lasts before it changes or disappears entirely. Pages update, servers go quiet, and entire small corners of the internet close without ceremony. Nothing marks the moment. It simply stops being there the next time anyone looks. A hard drive typically degrades and loses its data within 10 to 20 years. Magnetic patterns weaken, platters wear, and one day the drive simply stops answering. Engineers call this bit rot, a slow erosion, no different in spirit from rust on iron. Even our most modern memory is borrowed time. In Mesopotamia, cuneiform clay tablets have survived over 5,000 years. Baked hard by fire or simply dried in desert heat, these small tablets outlasted empires, languages, and the people who pressed their reed styluses into them. Clay, it turns out, remembers longer than almost anything else humans have made. Ancient Athens once staged thousands of plays, and almost all of them are gone. Only a small fraction of Greek drama survives, preserved mostly by chance copying through medieval monasteries. Sophocles alone is thought to have written over 100 plays. 7 remain. The rest exist only as titles in old catalogs, echoes of stories no one can read anymore. Let your breath find its own long line now. Notice the pause after each exhale, that small hush before the next breath begins. There is no need to shape it, only to follow where it already goes. Each breath a little longer than the last, each pause a little deeper, carrying you further from the noise of the day and closer to rest. Alexandria once held a library said to contain the accumulated knowledge of the ancient world. Scrolls on astronomy, medicine, mathematics, and poetry filled its halls, gathered from every port that traded with Egypt. Fires, wars, and centuries of neglect took most of it away. What remains today is only a fraction, fragments quoted by later writers who once held the originals in their hands. Over 90% of silent films made in the early 1900s no longer exist. Nitrate film stock was unstable, flammable, and often melted down to recover its silver content. Entire performances, entire careers, survive now only as a title in a studio ledger. A whole era of moving light and shadow has mostly dissolved into nothing more than memory of memory. DNA inside a human body begins breaking down almost immediately after death, and within a few thousand years it is usually gone entirely. Enzymes, bacteria, and moisture unravel the long molecular chains that once carried an entire person's blueprint. Under rare cold or dry conditions, traces can last longer. But for most of us, even our biological signature has an expiration built quietly into its structure. Stone grave markers wear smooth after a few centuries of rain, wind, and frost. Names carved with care become shallow grooves, then faint shadows, then nothing a fingertip can find. Old cemeteries are full of markers standing blank, their inscriptions surrendered long ago to weather. The stone remains upright, but whatever it once tried to say has already been carried off, letter by letter. Most human names fade from memory within 2 or 3 generations of death. A person's children may recall their voice. Their grandchildren might know only a name in a family tree. Beyond that, even the name itself often slips away, absorbed into vague phrases like an ancestor or someone long ago. Remembering, it turns out, has a fairly short reach. 4 generations, on average, is as far as family history travels without being written down. Beyond great-grandparents, most people can name almost no one, their stories and faces already unrecorded. Oral memory, however lovingly passed along, simply cannot hold an unlimited number of lives. Paper, ink, and photographs are what allow anyone to be known past that quiet boundary. Somewhere in the world, a language falls silent roughly every few months. Its last fluent speaker dies, and with them go words for plants, weather patterns, and ways of thinking that may exist nowhere else. Linguists sometimes arrive just in time to record a final voice speaking a tongue that no child will ever learn to answer in. Roughly half of all languages ever spoken by human beings have already vanished from the earth. Thousands of tongues that once carried entire worldviews now exist only as footnotes in linguistic archives, if they exist at all. Every lost language took with it a distinct way of naming rivers, kinship, and sky. The world grew quieter each time, without most of us ever noticing. Along the Nile Delta, a black stone slab carried 3 versions of the same royal decree, carved in 3 scripts. 2 were long known. The third, ancient Egyptian hieroglyphs, had gone unreadable for over 1,000 years. That single stone let scholars finally match sound to symbol, unlocking a script that would otherwise have remained a beautiful, permanent silence. Archaeologists estimate that 99% of human history left no written record at all. For most of our species' existence, no one carved a symbol, painted a wall, or pressed a stylus into clay. Entire lifetimes of hunting, gathering, loving, and dying passed without a single trace meant to be remembered. What survives from those vast stretches is mostly stone tools and scattered bone, mute witnesses to lives we will never truly know. Let your body grow heavy now, the way sand settles at the bottom of still water. Feel your feet first, sinking into the mattress, unwilling to lift again tonight. Let that heaviness climb into your legs, your hips, spreading like warmth through tired muscle. Your shoulders follow, releasing their grip on the day, dropping lower with each breath. Even your hands forget their purpose, resting open and unclenched. Let this weight carry you further down, past thought, into rest. Fingerprints and footprints erode within hours on most terrain, erased by wind, rain, or the next passing foot. A child's steps across wet sand vanish before the tide even returns. Even indoors, dust and foot traffic smooth away the marks we leave without noticing. The body writes constantly upon the world, yet almost none of that writing lasts past a single day. Cities, once alive with markets and voices, get buried beneath sediment over the span of centuries. Rivers shift, dust settles, and floods leave new layers of earth atop old foundations. Streets that once echoed with footsteps become quiet hills of soil, grazed by animals with no memory of what lies beneath. Entire settlements can vanish this way, not through destruction, but through simple accumulation. Pompeii lay hidden and forgotten for more than 1,500 years, sealed beneath layers of volcanic ash. Its streets, bakeries, and painted walls remained frozen in a single afternoon, untouched by time above ground. Generations lived and died over that buried city without knowing it existed. When excavation finally began, it was as though a moment-long thought gone had simply been waiting underground. Metal artifacts corrode into unrecognizable rust within a few thousand years, their sharp edges dissolving into flakes of orange and brown. A sword once carried into battle becomes a fragile crust, crumbling at the lightest touch. Bronze fares slightly better than iron, but even it eventually softens into green patina and dust. What was once forged with fire slowly returns to formless earth. Wood and other organic material typically decompose within a few centuries, given moisture, insects, and time enough to work. A wooden chest, a carved door, even a ship's hull will eventually soften and give way to fungus and rot. Unless buried in unusually dry sand or frozen ground, little of what was once alive as a tree survives long past its makers. Even the pyramids, built to outlast every empire that raised them, erode measurably within a few thousand years. Wind carries away grains of limestone one at a time, and sandstorms polish their edges smoother with each passing century. Their outer casing stones, once brilliant white, have long since been stripped or worn away. What stands today is already a diminished version of what was first built. Mount Rushmore, carved from resilient granite, is expected to erode away within a few million years. Rain and frost work slowly at its features, widening tiny cracks with each freeze and thaw. The monument's makers chose granite precisely because it resists weathering longer than most stone, buying the faces carved there an unusually long, though not endless, existence. Plastic in landfills can persist for centuries, resisting decay far longer than wood or metal ever could. Sunlight and time eventually break it down, not into nothing, but into ever smaller fragments that drift through soil, rivers, and air. It does not vanish so much as scatter, becoming a fine dispersed trace of the object it once was. Far above the atmosphere, human-made satellites keep their fragile orbits for only a few decades before drag and gravity pull them home. Even a satellite launched today will eventually spiral downward, burning apart in the same sky that once carried it aloft. Its metal frame turns briefly to fire, then to dust, scattered across ocean or atmosphere. Nothing manufactured for orbit was built to remain there forever. Radio signals leaving Earth have traveled only about 100 light-years outward, a modest distance on the scale of a galaxy stretching 100,000 light-years wide. Our earliest broadcasts, decades of voices and music, form a thin bubble expanding at the speed of light. Beyond that bubble, the universe has never heard a single human word. It is, for now, a small and private silence. Somewhere beyond these walls, a low hum rises and fades, wind against a window or the settling creak of an old house cooling for the night. You don't need to name it. Let it arrive. Hold for a moment and pass on, the way sound always does when nothing holds it in place. Your breath can follow the same pattern, rising, pausing, releasing, asking nothing of you but to keep going. In 1974, scientists at the Arecibo Observatory sent a radio message toward a cluster of stars 25,000 light-years away. Encoded in simple binary, it described numbers, Denon, and the shape of a human being. The message will not arrive for another 25 millennia, and any reply would take just as long to return. It was less a conversation than a message in a bottle, cast into an ocean too wide to answer soon. The Voyager Golden Record, a gold-plated disc carrying sounds and images of Earth, could remain playable for as long as 1 billion years in the vacuum of space. No wind, no rust, no bacteria exist there to wear it down. Long after every library and monument on Earth has crumbled, this small disc may still be circling, carrying greetings recorded by people who no longer have names anyone remembers. Voyager 1, humanity's most distant spacecraft, will not pass near another star for roughly 40,000 years. It drifts now through the near emptiness between stars, carrying no memory of the world it left, only instruments falling silent one by one. By the time it nears anything resembling a sun again, the constellations we know will have rearranged themselves into shapes no one alive today has seen. The Pioneer plaques, gold anodized panels fixed to 2 1970s spacecraft, rank among the most durable objects humans have ever made. Etched rather than painted, their images of a man, a woman, and our solar system's location resist the decay that erases paper, film, and flesh. Drifting silently beyond the planets, these small metal plates may outlast every statue, book, and building left behind on Earth. Nuclear waste storage sites are marked with warning symbols engineered to remain legible for 10,000 years, a span longer than written language itself has existed. Designers imagined future visitors who might not read any current alphabet, and so relied on stark shapes, spikes, and forbidding fields of stone. Whether such warnings will still make sense to whoever finds them remains an open question. Of the 7 wonders once listed by ancient travelers, only the pyramids of Giza still stand largely intact. The Hanging Gardens, the lighthouse, the great statue of Zeus, all vanished long ago, leaving only descriptions in old texts. The pyramids endure not because they were built better, but because the desert around them offered little rain, few earthquakes, and few reasons for later builders to tear them down for stone. Continents drift a few centimeters each year, a pace too slow to notice, yet powerful enough to erase most surface evidence of human civilization within about 100 million years. Mountains will rise where oceans now sit, and today's coastlines will fold into terrain unrecognizable to any future eye. The ground beneath every city will eventually travel somewhere else entirely, carrying its secrets with it. Beneath every ocean, the seafloor is born at ridges and swallowed again at trenches, a slow conveyor belt of stone. Within 200 million years, nearly all of today's ocean crust will have been drawn back into the mantle and remade. Nothing on the seabed is truly permanent, no matter how deep or how still it appears from above. The water stays, but the floor beneath it keeps changing hands. Rain, wind, and icework on rock without pause, carving away roughly the height of Mount Everest from every continent over just a few million years. This wearing down happens grain by grain, invisible in a single lifetime, undeniable across geologic time. Rivers carry the fragments to the sea, where they settle into new layers of stone. What looks eternal from a mountaintop is, in truth, already mid-journey toward becoming sand. Every mountain range standing today, however sharp its peaks now appear, will be worn down to gentle hills within tens of millions of years. The Himalayas, the Andes, the Rockies, none are exempt from this patient leveling. Uplift and erosion trade places again and again, but erosion always wins the final round. What remains eventually is not a peak, but a plain, waiting for something new to rise. Let warmth begin at your feet, spreading upward the way morning light moves across a floor. Feel it settle into your ankles, then rise through your knees, unhurried, like something poured rather than switched on. Let it reach your chest and shoulders, loosening what the day left tightened there. Let it climb into your jaw, your brow, your closed eyes, until your whole body feels held in the same low, even warmth, and there is nothing left to do but rest inside it. Fossils form only under rare, exacting conditions: rapid burial, the right minerals, and absence of oxygen, enough time undisturbed. Most living things die and simply return to soil, leaving no trace at all in the rock record. A body must be buried quickly before scavengers or decay erase every soft detail. Because of this, the fossil record is less a full story than a scattering of surviving pages. Across the entire span of life on Earth, fewer than 1 in 1,000 species that ever existed have left a fossil anyone has found. Countless creatures lived, bred, and died, leaving nothing but a brief ripple in an ancient ecosystem. Paleontologists study a record built from exceptions, not averages. The vast majority of life's history remains, and will likely remain, unknown. Because fossilization is so rare, human remains will likely be an uncommon find for whatever intelligence studies Earth's rock millions of years from now. Most bodies decompose fully, leaving nothing but scattered minerals absorbed back into soil. Only a fraction, buried in just the right sediment, might harden into something a future excavation could ever uncover. Humanity's physical trace in stone may be thinner than most people imagine. Geologists already speak of a layer forming now, one that will preserve unmistakable evidence of human civilization long after our cities are gone. Aluminum, concrete, plastic, and altered soil chemistry are settling into sediment worldwide, forming a distinct band future strata will hold. This layer, however thin, will mark a boundary as real as any left by ancient volcanic ash. It is a record written not in words, but in materials themselves. Traces of mid-20th century nuclear testing appear as a faint radioactive signature spread across the planet's soil and ice. This layer of unusual isotopes marks a moment so distinct that geologists use it as a reference point for dividing eras. It settled quietly into glaciers, sediment, and tree rings around the globe. Long after every document about that era fades, this faint chemical fingerprint may still remain readable in stone. Concrete and plastic, ordinary materials of daily life, may harden into detectable rock layers lasting millions of years into the future. Concrete can fossilize much like natural stone, while plastic fragments compress into a strange synthetic kind of sediment. Long after cities crumble, these materials could remain embedded in cliffs and riverbeds as an unmistakable marker of an industrial age. It is a strange kind of permanence, born from things meant to be temporary. Coastlines will not simply flood once and stay still. Across hundreds of millions of years, ice ages will come and go, pulling sea levels down and pushing them back up again and again. Cities built along today's shores will vanish beneath waves, resurface as dry land, and vanish once more. The ocean's edge is not a boundary, but a slow, rhythmic breathing. Roughly 250 million years from now, Earth's wandering continents will drift back together into a single landmass. Geologists have given this future world a name, Pangaea Proxima, though its exact shape remains a matter of ongoing calculation. Oceans will close, mountain chains will rise where seas once spread, and a new center of the world will form. The map familiar to us today is only a brief arrangement in a much longer dance. By that same distant era, almost nothing about Earth's surface will look as it does now. Rivers will carve unfamiliar paths, deserts will spread where forests once stood, and entirely new mountain ranges will rise from the meeting of drifting plates. Whatever coastlines or valleys hold meaning today will have long since dissolved into other shapes. The planet keeps its name, but very little of its face. High above, the moon is drifting away from us, inch by inch, at about 3.8 centimeters every year. It is a distance too small to notice in a lifetime, yet vast enough to reshape the sky over millions of years. The tides that once pulled sharper and stronger will loosen their grip gradually. Night by night, our nearest companion is easing itself into a wider orbit. Somewhere, mist is settling over still water, thinning and thickening, without any hurry to arrive anywhere. It does not need a shape to hold, only the slow permission to drift where the air takes it. Your breath can move the same way now, rising and settling without direction, without effort. Let it spread outward like that mist, until the edges of you feel less certain, less needed, less awake. Earth is turning a little slower than it used to. Each century, the day lengthens by a tiny fraction of a second, so gradually that no single lifetime could ever feel the change. The moon's gentle pull is the quiet cause, drawing energy from our spin as it drifts farther away. Millions of years from now, a full day on Earth will last noticeably longer than it does tonight. About 600 million years from now, the sky will lose one of its rarest sights. As the moon continues its slow retreat, it will eventually appear too small in the sky to fully cover the sun. Total solar eclipses, the kind that darken the day and reveal the corona's pale glow, will simply stop happening. Future generations, whoever or whatever they may be, will only read about a spectacle we still get to witness. The sun is growing brighter with time, a slow and steady increase in its output that stretches across ages. In roughly 1 billion years, that added warmth will be enough to boil away Earth's oceans entirely. Water vapor will thicken the atmosphere, trapping even more heat until the seas that once covered most of the planet simply disappear into space. The blue world will not stay blue forever. Once the oceans are gone, the plants and microorganisms that depend on liquid water to convert sunlight into energy will lose their means of survival. Photosynthesis, the quiet engine behind nearly all life on Earth, will become impossible within roughly 1 billion years. Forests will thin into dust, and the green that once covered continents will fade from the record entirely. The planet's air itself will slowly forget how it once smelled of leaves. Earth's magnetic field, generated deep within its molten core, will not shield the atmosphere indefinitely. As the planet's interior cools over billions of years, that protective field is expected to weaken and eventually fail. Without it, solar wind would strip away the atmosphere in a slow, steady erosion, much as it likely did to Mars long ago. The sky that has always sheltered us depends on a fire burning quietly far below our feet. In about 5 billion years, the sun will swell into a red giant, its outer layers ballooning outward as hydrogen fuel runs low in its core. The surface will cool and redden even as the star's overall brightness climbs enormously. Its diameter could stretch across what is now the orbit of Earth. The steady yellow star that has lit every human century will become something wider, dimmer at its skin, and far stranger to look at. As the sun's atmosphere reaches outward, Mercury and Venus sit closest in its path. Both worlds are expected to be swallowed by the swelling star, their rocky surfaces vaporized within its outer layers. Mercury, scorched already by proximity, offers little resistance. Venus, thick with cloud, would lose its cover in moments compared to the age it took to form. Two of the solar system's oldest neighbors would simply become part of the sun once more. Earth's fate during this expansion is not fully settled among astronomers. The planet may be pulled inward as the Sun loses mass and its gravity weakens, letting Earth drift to a slightly wider orbit. Even so, the increased heat would likely boil away any remaining atmosphere and surface material long before the Sun's edge arrives. Whether swallowed outright or merely scorched to bare rock, Earth's story as a living world ends here. Shedding its outer layers, the dying Sun will scatter gas and dust into space, forming a brief and glowing planetary nebula. Ultraviolet light from the exposed core will ionize this expanding shell, painting it in colors of green and pink for a few tens of thousands of years. Such nebulae are common sights around other aging stars in the galaxy tonight. What remains after the glow fades will be far smaller than the star that made it. A white dwarf is what remains once the nebula disperses, a dense Earth-sized core made mostly of carbon and oxygen. No fusion will occur inside it any longer, only leftover heat radiating away across unimaginable stretches of time. It will cool by degrees, fading from white to yellow to a dim, dark ember over trillions of years. This small ember is the final chapter of the star that once anchored our entire sky. Let the jaw loosen now, just slightly, teeth parting without effort. Feel the muscles around the eyes give up their hold, eyelids growing heavier with each breath that passes. Behind closed eyes, there is only a soft, shifting dark, no need to watch for anything there. Let the forehead smooth, the temples release, the whole face resting like something set down at the end of a long day. Nothing here asks to be held. Any artifact left on Earth's surface, plaques, statues, buried time capsules, would not survive the Sun's later expansion. Metal would melt, stone would crack and vaporize, and the very ground holding them would be stripped away by heat. Nothing engraved with human intention was built to outlast a star. Whatever message we hoped might endure would need a different kind of shelter than the planet that made it. Voyager 1 and Voyager 2, launched in 1977, are already farther from Earth than any human object has traveled. Long after the Sun swells and fades, these two spacecraft may still be moving through the space between stars, carrying their golden records forward. Neither depends on Earth's gravity or the Sun's light to continue. In a modest way, they could outlast the very world that built them. Interstellar space contains almost nothing, just a handful of atoms per cubic meter across vast, cold distances. Without dense matter to collide with, a spacecraft like Voyager could drift for eons without meaningful damage to its structure. There is no wind out there, no rust, no erosion of the kind that wears down everything on a planet's surface. Between the stars, an object built by human hands might simply keep going, undisturbed, for longer than the Sun itself will last. The Milky Way is already falling toward its neighbor, the Andromeda Galaxy, closing the distance between them by about 100 kilometers every second. In roughly 4.5 billion years, the two galaxies are expected to meet and begin merging into one another. Stars will not likely collide, spread too thinly across such distances, but the shapes of both galaxies will be pulled and reshaped over hundreds of millions of years. Astronomers have already given this future galaxy a name, Milkomeda, a blend of the Milky Way and Andromeda. It will not look like either galaxy does now. Over hundreds of millions of years, the two spiral shapes will lose their neat arms, twisting into a single, rounder form. New stars will still form inside it, born from gas stirred loose by the encounter, even as older stars settle into unfamiliar orbits. Despite two galaxies passing through one another, actual collisions between stars will almost never happen. The distances separating stars are so vast that even trillions of them can pass close without ever touching. A single star and its nearest neighbor might be separated by tens of trillions of kilometers, an emptiness so wide that galaxies can overlap like mist through mist, mostly undisturbed. Any interstellar probe still drifting when the merger begins would be swept into new, unpredictable paths. Gravitational tides from both galaxies would tug at its trajectory, bending a once steady course into something no engineer could have charted. It might be pulled toward the galactic core or flung outward into deeper space. Its golden record would keep traveling, simply toward a destination no one on Earth ever chose for it. Observers on any surviving world would see a sky utterly transformed. Familiar constellations would dissolve, replaced by denser fields of stars and a brighter, more diffuse band of light overhead. Andromeda, once a faint smudge in a dark sky, would eventually spread and blend until it was simply part of the galaxy itself. Whatever eyes looked upward then would find no trace of the sky we know tonight. Gas clouds within the newly merged galaxy will keep feeding fresh stars for a long while, but not forever. Each burst of star formation consumes some of that raw material, and mergers tend to trigger especially vigorous bursts early on. Eventually, the available hydrogen and helium will thin out, and the pace of new star birth will slow, then fade, like a fire settling toward its final embers. Most stars in the universe today are not bright giants like our Sun, but small, dim red dwarfs. They make up the majority of stars in nearly every galaxy, quietly outnumbering all other types combined. Faint and unremarkable to the eye, they burn their fuel with such restraint that they will still be shining long after suns like ours have faded into cooling embers, trillions of years from now. Notice the small pause between one breath and the next. There is no need to shape it, only to let it happen on its own. As you exhale, let the breath grow a little longer than the one before it, unhurried, without effort. Each inhale can arrive quietly. Each exhale can trail a little further into stillness. Let your shoulders follow that same slow lengthening, sinking a fraction more with every breath that passes. 10 trillion years is roughly the lifespan expected of a typical red dwarf star, an almost unimaginable stretch compared to the 10 billion years our own Sun will manage. These small stars fuse their hydrogen so slowly and evenly that they sip at their fuel rather than burn through it. Long after brighter stars have died and cooled, red dwarfs may still glow faintly, patient furnaces outlasting nearly everything else formed in their era. By the time the universe reaches roughly 100 trillion years of age, cosmologists expect the last new stars to form. Gas reserves across galaxies will have thinned past the point of collapsing into anything new. After that threshold, no fresh light will be born from clouds of hydrogen again. Whatever stars exist then will be the final generation, and the galaxies around them will slowly stop producing anything new at all. After star formation ends, galaxies will hold only what is left behind: white dwarfs, neutron stars, and black holes, the quiet remnants of stars that once burned brightly. No new light will replace the old. Slowly, galaxy by galaxy, these remnants will dim, cool, and drift apart from one another, each one a faint marker of a star that used to shine, keeping its shape long after its fire has gone out. White dwarfs will cool into cold black dwarfs over roughly 1,000 trillion years. Once a star's nuclear fires stop, only residual heat remains, radiating out into the dark. That process is so gradual that no black dwarf has ever actually formed yet, anywhere in the universe. Every white dwarf that exists today is still cooling, still glowing dim red or white, waiting out an epoch longer than the universe's current age many times over. Neutron stars endure long after ordinary stars have died, dense remnants no larger than a city yet heavier than the Sun. Formed in the collapse of massive stars, they hold their shape through a strange balance of quantum pressure resisting gravity's pull. Long after white dwarfs have cooled to near nothing, These ultra-dense spheres will still spin in the dark, some slowing over eons, others locked into steady rotation. Brown dwarfs occupy a strange middle ground, too small to sustain full hydrogen fusion, but large enough to burn deuterium for a very long time. Some may continue that dim fusion for trillions of years into the future, far outlasting brighter stars. They never ignite the way true stars do, glowing instead with a low, reddish light, drawn from their own contraction and slow nuclear burn. Their patience is almost geological in scale. Over spans reaching into the quintillions of years, planetary orbits gradually come undone. Tiny gravitational nudges from passing stars accumulate, bending paths that once seemed fixed. Given enough time, this cumulative pull can unanchor entire planetary systems from their orderly arrangement. What looks stable across a human lifetime is only stable in that narrow window. Across cosmic time, orbits are always slightly restless. Close encounters between stars will eventually scatter most planets away from the worlds that once held them. As galaxies age and stars drift near one another, gravity occasionally flings a planet out of its orbit entirely, sending it into the emptiness between stars. Over long stretches of time, this process repeats across countless systems. Free-floating planets, untethered from any star, may eventually outnumber the ones still orbiting something. The local group, our small cluster of galaxies bound together by gravity, will not be pulled apart by the universe's expansion. The Milky Way, Andromeda, and dozens of smaller galaxies are close enough that their mutual pull overpowers the pull of the wider cosmos. Whatever new form they merge into, this cluster will hold itself together as an island, even as the wider universe pulls farther away. Beyond the edge of that gravitationally bound cluster, cosmic expansion will carry everything else away. Every galaxy outside the local group sits on a current that widens with time, moving apart from us and from each other. There is no force strong enough at that distance to resist the stretching of space itself. In time, our island of galaxies will be the only one left within reach. Let your body grow heavy now, one part at a time. Feel the weight of your legs sink into the mattress, as if the bed were rising to meet them. That same heaviness can spread into your arms, your hands, each finger loosening its hold on anything at all. Your head rests fuller into the pillow, your jaw unclenching, your eyelids thick with sleep. There is only this heaviness now, spreading, welcome, asking nothing of you but to be felt. Galaxies far enough away are already receding faster than light itself, a consequence not of motion through space, but of space expanding between us. Nothing physical breaks any speed limit. The fabric carrying those galaxies simply grows. Light from such galaxies, once it began its journey toward us, may never complete the crossing. Some of what we see tonight is already gone beyond that boundary, sliding past our reach without ever knowing it. In about 100 billion years, light from galaxies beyond our own may fade past any hope of detection. As expansion carries them beyond the horizon we can observe, their glow stretches and thins until no telescope, however patient, could gather it. Future astronomers, born into that era, might look up and find only the stars of one merged galaxy, unaware that countless others ever existed at all. Dark energy is quickening the expansion of the universe rather than easing it, pushing space to spread faster with each passing age. Gravity alone would have pulled everything back together, but this unseen pressure overwhelms that pull. It grows stronger, relatively speaking, as matter thins out across the widening cosmos. The push has no known limit, and nothing yet observed seems able to stop it. If that pressure holds steady across the ages, the observable universe will shrink down to just our local group. Everything beyond its gravitational hold will slip past the horizon we can ever reach. What remains will be an island of a few dozen galaxies, bound together while the rest of creation recedes forever. From within it, the night sky will hold less and less to see. Civilizations arising long after ours may find no evidence that other galaxies ever existed at all. Their telescopes, however patient or powerful, would gather only the light of their own merged home. No record, no glow, no whisper of the vanished galaxies would remain to study. They might reasonably conclude the universe had always been small. Redshift will eventually stretch every remaining photon in the cosmos to wavelengths longer than the observable universe itself. Light, that once carried color and information, will thin into something undetectable, beyond the reach of any possible instrument. Even the idea of light, as we understand it now, will lose its meaning. What began as radiance ends as nothing measurable at all. Even the afterglow of the Big Bang, the ancient light that still bathes the universe today, will fade past detection. That glow, already stretched into microwaves after billions of years, will thin further until no receiver could ever catch it. The oldest light in existence will simply become too faint a whisper to hear. Its story will end not with destruction, but with silence. Galaxies will drift so far apart that crossing between them becomes physically impossible, no matter what technology might exist. The distances will outrun any signal, any ship, any beam of light sent to bridge them. Space itself will have grown too wide for reaching. Whatever civilizations remain will be sealed within their own island, alone by the nature of geometry itself. Across roughly 100 billion years, gravitational encounters will fling stars out of their home galaxies, one by one. Each near pass between stars nudges orbits, and over such spans, enough nudges send stars sailing into the emptiness between galaxies. Slowly, the galaxies will thin, losing their brightest members to the dark. What once looked crowded with light will empty out star by star. At the heart of every galaxy, a supermassive black hole will draw in what remains, the last stars, the last clouds of gas, until the center holds nearly everything. Over unimaginable stretches of time, orbits decay and matter spirals inward, feeding a hunger that never quite ends. The galaxy's shape will hollow out around it. Where billions of stars once turned, only a single dark point will remain. Somewhere beyond the room, a low hum rises and fades, the kind a house makes when it settles into night. It comes and goes without hurry, like breath moving through old walls. Let your attention follow it out and back, until the space between each rise grows longer. There is nowhere this sound needs to take you. It only comes near, and then it goes, and you can go with it into rest. Stellar mass black holes will come to hold most of a galaxy's remaining mass, outnumbering every other kind of star or remnant left behind. As lighter stars fade or scatter, these dense relics of collapsed giants will dominate what's left. A galaxy in this age will be less a field of light than a scattering of dark, heavy points. Its brightness will belong to the past. Protons, the building blocks of every atom, may not last forever. If proton decay occurs, it would happen only after stretches of time longer than 10,000 trillion years, written as 10 to the 34th power. Across such an age, matter itself would come undone, atom by atom, until nothing solid remained. No rock, no bone, no page would survive that long. Whether protons decay at all remains an open question in particle physics. If they prove stable, ordinary matter could persist in altered forms for spans beyond imagining. Rocks might crumble to dust, dust might thin into gas, but something built from atoms could remain. The universe would carry matter forward, reshaped again and again, long after every star has gone dark. Black holes, once thought eternal, are theorized to fade. A physicist named Stephen Hawking showed that black holes emit radiation at their edges, letting mass escape a little at a time. Over immense stretches of time, this radiation carries away a black hole's substance entirely. What seemed like the universe's most permanent objects turn out to have an ending of their own. A black hole, the mass of our Sun, would take about 10 to the 67th power years to evaporate completely. That number dwarfs the current age of the universe so thoroughly that comparison becomes almost meaningless. Long after every star has died, long after galaxies have emptied, such a black hole would still be leaking its last light into the dark. The largest black holes, holding the mass of billions of suns, could take up to 10 to the 100th power years to vanish, a number sometimes called a googol. Even in a universe already emptied of stars and galaxies, these giants would remain, holding their darkness together, outlasting nearly everything else that ever existed. When even the largest black holes finish evaporating, an age astronomers call the black hole era comes to a close. It will have lasted longer than every era before it combined, longer than the age of stars, longer than the age of galaxies. Its ending marks a threshold, the last dense, structured objects the universe will ever hold, dissolving into light. Past that threshold, what remains is thin and scattered, stray photons, electrons, neutrinos, drifting apart from one another across distances too vast to measure. No stars, no planets, no black holes. Only a mist of particles and radiation spread so thin that encounters between them become exceedingly rare. In this emptied age, strange pairings may still occur. An electron and its antimatter twin, the positron, can briefly bind together into something called positronium, a fleeting atom made of no ordinary matter at all. Such unions form rarely and dissolve quickly, tiny sparks of structure in an otherwise formless dark. Cosmologists give this coming age a name, the Dark Era. In it, light particles called photons and light matter particles called leptons drift through space so empty that structure, as we understand it, ceases to exist. No light source remains to shine. Only ancient radiation stretched thin, wandering through a universe grown almost featureless. Let warmth begin somewhere small, perhaps behind your eyes or low in your chest, and let it spread from there, unhurried, the way sunlight moves across a floor in late afternoon. Let it reach your shoulders, loosening what they carry. Let it move down through your arms, into your hands, until your fingers feel heavy and full. Let it settle in your legs, your feet, until warmth is simply where you are, and rest is what's left. Most of the disorder in today's universe is not held in stars at all, but in supermassive black holes. Each one carries an entropy so immense that it dwarfs the combined disorder of every star, planet, and cloud of gas in its galaxy. Astrophysicists calculate that these dark giants, though few in number, account for the overwhelming share of entropy across the cosmos. Disorder, it turns out, gathers most densely where light cannot escape. Physics carries a rule so consistent it has never once been observed to fail. Disorder tends to increase. This is the second law of thermodynamics, quietly governing everything from a cooling cup of tea to the slow unraveling of galaxies. Energy spreads out, structure loosens. Given enough time, arrangement gives way to scatter. It is not a punishment, only a tendency, patient across the ages. There exists a theoretical ceiling to disorder, a point beyond which entropy can climb no higher. Physicists call this state heat death, the endpoint the second law quietly points toward. At maximum entropy, everything that could spread apart already has. No further change moves things toward greater disorder, because there is nowhere left for disorder to go. Heat death names a condition where no usable energy gradients remain anywhere. Everything sits at the same temperature, the same density, the same nothing in particular. Without differences to draw on, nothing can flow, nothing can do work, nothing can power a process of any kind. Energy still exists, technically, but it has become entirely unusable, spread too evenly to move. Under these conditions, no work can happen. No information can be processed. No life, in any form we understand, could persist. A mind requires contrast to think. A body requires gradients to metabolize. A machine requires differences to compute. Heat death removes every contrast at once, leaving a universe that simply is without doing anything further. Storing even a single bit of information requires a difference somewhere, a hot spot beside a cool one, a signal distinguishable from its background. As entropy approaches its maximum, these temperature differences dissolve. Without them, nothing can hold a distinction long enough to count as memory. The universe, in this sense, loses its capacity to keep anything distinct from anything else. Memory is not an abstract thing floating free of matter. It lives in arrangements, neurons wired a certain way, magnetic domains pointed a certain direction, atoms held in a particular pattern. Entropy works against every such arrangement, nudging structure toward disorder over time. A memory, physically speaking, is simply an organized shape resisting the pull toward sameness for as long as it can. There is a principle in physics stating that information can never truly be destroyed, only rearranged into forms too scrambled to read. A burned letter's atoms and photons still, in theory, carry every trace of what was written, dispersed into smoke and heat and light. Recovering it would require tracking an almost unimaginable number of particles. The information persists, legibility does not. Physicists have long debated what happens to information that falls into a black hole. The black hole information paradox asks whether that information is lost forever behind the horizon or whether it somehow escapes encoded in the radiation the black hole slowly emits. No resolution has yet satisfied everyone in the field. The horizon guards its secret carefully. Landauer's principle draws a quiet line between information and physics. Erasing even a single bit of information requires a minimum, unavoidable release of heat into the surrounding environment. Forgetting, in other words, is never entirely free. It costs entropy, however small. Every act of erasure, human or cosmic, leaves a tiny thermodynamic trace behind, however impossible it may be to detect. Let the sound of your own breath become the only tide you follow tonight. Somewhere far off, a shoreline is drawing water back into itself, slow and unhurried, leaving smooth sand behind. You don't need to watch it happen. Just notice the rhythm, in and out, matching the pull and release of something ancient and larger than this room. Let your body settle into that same slow rhythm and rest. Black holes, it turns out, are remarkably forgetful. Physicists describe this with something called the no-hair theorem. No matter what falls past the horizon, planets, stars, spacecraft, only three properties survive: mass, charge, and spin. Every other detail, every shape and history, is erased from the outside view. A black hole cannot tell you what it swallowed. It only tells you how much, and how it now spins. Not everyone accepts that anything is truly lost. A number of physicists argue that whatever information the universe was born with at the Big Bang must, in some form, persist for as long as the universe exists. Rearranged, diluted, scattered across unimaginable distances, perhaps, but never fully gone. The debate remains unsettled, one of the deepest open questions in theoretical physics. The holographic principle offers a strange kind of comfort. It suggests that everything happening inside a volume of space, every event, every particle, might be fully described by information encoded on that region's outer boundary, like a shadow containing the whole shape of what cast it. If true, nothing occupying 3 dimensions would ever be lost, only projected differently, written on a surface instead of held within a depth. There is a theorem, named for the mathematician Henri Poincaré, describing something almost dreamlike. Any system with finite energy confined to finite space will, given enough time, return arbitrarily close to a state it once occupied. Not exactly the same, but near enough to seem familiar. The universe, if finite in this sense, could someday drift back toward a shape resembling one it has already worn. Given an infinite stretch of future, even the smallest fluctuations in empty space begin to matter enormously. Quantum theory allows particles to appear briefly from nothing, guided by probability rather than certainty. Stretch that possibility across a truly endless timeline, and rare events stop being rare. In principle, any configuration of matter, however improbable, could eventually flicker into being again, purely by chance. Among the strangest ideas to emerge from this thinking is something physicists call a Boltzmann brain. Named after the physicist Ludwig Boltzmann, it describes a fully formed thinking mind assembling itself for an instant out of random thermal fluctuations in empty space, with no body, no history, no universe around it, just a flicker of awareness appearing from the vacuum and dissolving again just as quickly. If the universe truly lasts forever, the numbers grow uncomfortable. Given enough time, these randomly fluctuating minds could vastly outnumber every observer who ever evolved through the ordinary path of stars, planets, and biology. It's a strange thought experiment, one physicists use to test their assumptions about probability and time, rather than a claim about what tonight actually holds. Space itself may not be as settled as it appears. Certain models in particle physics suggest the vacuum we inhabit could be a false vacuum, a low point that only seems stable, sitting above a deeper, truer minimum of energy. If a bubble of that true vacuum ever formed, the laws of physics, as we know them, could change abruptly within it, without warning, without cause visible beforehand. Should such a bubble ever form, it would not creep. It would expand outward at the speed of light, the fastest anything can travel, converting the old vacuum into the new as it went. Nothing could outrun it, and nothing inside its reach would receive warning before arrival. It remains, for now, only a theoretical possibility, one among the universe's many quiet, unresolved questions. Vacuum decay, should it ever occur, would not simply end matter, it would erase the very rules by which anything could be recorded. No archive would remain, no photon carrying a message, no structure capable of holding a memory. The transition would be absolute, converting the old vacuum into a new one where different laws applied, or perhaps none capable of supporting information at all. Nothing would be spared to bear witness afterward. Let your jaw loosen, just slightly, the way a hand opens when it forgets it was ever closed. Behind your closed eyes there is only a low, dim field, no shapes asking to be seen. Your eyelids rest with their full, unhurried weight, needing nothing else to hold them there. Let your face become unreadable to anyone watching, smoothed of any expression, simply resting, simply present, drifting further from thought with each unremarkable breath. Cosmic inflation, the sudden stretching that shaped our early universe, may have already erased whatever came before it. If a prior state existed, inflation's rapid expansion could have diluted its imprint beyond any possible detection. Cosmologists studying the earliest light, left over from the Big Bang, find no confirmed trace of anything older. Whatever preceded our universe, if anything did, may be permanently unreadable, smoothed away by the same stretching that made room for stars. Certain theoretical frameworks propose that our universe is only one among an unimaginable number, each with its own laws, its own history, its own ending. This idea, called the multiverse, arises naturally from some versions of inflationary theory, where expansion never fully stops everywhere at once. Other bubble universes may be forming even now, endlessly, each sealed off from ours, by distances that stretch beyond meaning. It remains an open question whether such universes could ever be observed at all. If multiverses truly exist, then our universe's eventual fading may not be a singular tragedy, but simply one ordinary event among countless others. Other bubbles might be forming, evolving, and dissolving in parallel, each with its own stars, its own silence to come. The disappearance of any single universe, ours included, would carry no special weight within a landscape built from infinite repetition. Loss, in this view, becomes almost commonplace, woven into the fabric of everything. Cyclic universe models offer a different picture entirely, one where the cosmos does not end but repeats. In these theories, expansion eventually reverses, matter and energy contract back together, and from that contraction a new universe emerges, beginning the cycle again. Some versions imagine this happening endlessly, without any true first beginning. The universe, in this telling, becomes less like a single story, and more like a long, echoing rhythm. Within these repeating models, each collapse would likely erase the fine details of what came before. Galaxies, memories, entire histories of thought and light, compressed and scrambled beyond recognition as the next cycle begins. Whatever new universe emerged afterward would carry no record of the one before it. The rhythm continues, but each verse forgets the one that came earlier, starting fresh from an unmarked point. The Big Crunch describes what such a collapse might actually resemble if it ever came to pass. Every galaxy, every star, every fragment of matter and radiation drawn inward, compressed together into a single point of unimaginable density. Space itself would fold inward, rather than stretch outward, reversing billions of years of expansion in a final, silent convergence. Whatever information existed would be crushed past any possibility of reconstruction. The measurements gathered so far, though, point in a different direction. Distant supernovae, studied carefully over recent decades, reveal an expansion that is accelerating rather than slowing toward reversal. Current evidence favors a universe that keeps stretching outward indefinitely, not one destined to collapse back upon itself. The Big Crunch remains a mathematically possible outcome, but not the one our observations currently support. Certain theoretical models suggest another possibility tucked inside collapsing stars. When matter compresses into a black hole's singularity, some physicists propose that instead of ending entirely, it might tunnel through into an entirely new expanding region, a baby universe branching off from our own. If true, endings and beginnings could be quietly connected everywhere, each collapse seeding growth somewhere else, unseen and unreachable from where we stand. Even if every fragment of information from the universe's history survives, unscrambled and complete, that survival alone may not be enough. Information needs a reader, a mind, a system able to unpack its pattern into meaning. In the far future, when structures thin into scattered radiation, no such reader might remain. The record could exist and matter equally little, like a book left open in an empty room. The distinction between preserved and understood grows harder to draw as the eras pass. An observer, in the language of physics, is anything capable of registering change and recording a result. After heat death, with no temperature differences and no structure left to shift, that capability disappears along with everything else. Watching requires a system distinct enough from its surroundings to notice a difference. Once every particle drifts at the same faint temperature, no such distinction can exist. The question of who is watching stops applying, because watching itself no longer has a foothold. Let your attention rest on the space between one breath and the next tonight. Notice how the inhale arrives without effort, and how the exhale, if you let it, grows a little longer each time. There is no need to guide it, only to notice it lengthening, easing the shoulders as it goes. Each breath out can carry a small piece of the day's weight with it. Let the pause after each exhale widen, an easeful stillness settling into the body, breath by breath, until sleep arrives on its own. Time itself may lose any operational meaning once no change, no motion, no process occurs anywhere within it. Physicists build every clock, every calendar, every rhythm of measurement on something happening, some difference between one instant and the next. Remove all motion, and the ticking that once marked seconds finds no event left to click against. In such a stilled universe, time might still exist mathematically, yet carry no practical function at all. It becomes a line drawn through a blank page, with no marks to divide it into before and after. Without change, there would be no way to measure or mark how much time has actually passed. A clock depends on some repeating motion, a pendulum, a vibrating atom, a planet circling a star. Strip away every one of those motions, and duration stops being something you could point to or count. Even light, if it stopped moving between 2 points, would leave no interval to measure. Time might continue in name only, drifting past unregistered, its passage no different from its absence. Physicists still debate whether an eventless universe can truthfully be said to have a future at all. Many argue that a future requires at least the possibility of something happening within it, a fork in the road not yet taken. Others suggest the mathematics of space-time allows a future to exist as a structure, regardless of whether anything ever unfolds inside it. The disagreement sits at the edge of physics and philosophy, where equations and meaning no longer perfectly agree. No resolution has yet been reached, and perhaps none ever will be. Some cosmologists frame the universe's slow forgetting as a matter of thermodynamics, never intention. There is no design behind the fading, no verdict passed against memory or meaning. Entropy simply increases, as physics predicts it must, spreading energy until no gradient remains to hold a pattern together. What looks from a human vantage like loss or erasure is, from the universe's vantage, simply balance being restored. The forgetting carries no judgment, only the steady math of heat finding its level. Memory, described in the language of physics, is only a structure that manages to resist entropy for a while. A carved name, a stored photograph, a brain's neural pathway, each is an arrangement holding its shape against the pull toward disorder. Given enough time, every one of these arrangements loses its edges and blends into the surrounding noise. What we call remembering is really a temporary victory, small and local, against a much larger and much older tendency toward forgetting. Every memory borrows its permanence briefly from a current running the other way. Human civilization, weighed against the full span of cosmic time, is best understood as a brief, localized dip in entropy. For a few thousand years, matter organized itself into cities, languages, ideas, and machines, resisting disorder in a small corner of one ordinary galaxy. Against the vast increase of entropy elsewhere in the universe, this pocket of order is real, but tiny and temporary by any cosmic measure. It is a ripple of pattern rising briefly from a much larger, much stiller sea. The ripple matters completely to those living inside it, even as the sea barely notices. The entire span of human existence, set against the age of the universe, occupies a fraction of time almost too small to register. If the universe's whole history were stretched into a single year, humanity's entire story would occupy only its last few seconds. Every war, every love, every book ever written would fit inside that narrow sliver near the end. It does not make that story smaller to hold it, only to notice how much larger the surrounding silence has always been. The proportion is staggering, and strangely, it asks for no despair. A black dwarf star, the coldest and final ember of a sun-like star, takes over a quadrillion years merely to form. Once formed, it will drift through space far longer than that, fading by degrees into near absolute darkness. Every trace of humanity, every language, every grave, every satellite will have vanished long before such a star finishes cooling. Against its patient timescale, our entire history barely registers as a flicker. The star does not notice. It simply keeps growing colder, in the dark, alone. Whether the universe truly forgets may depend less on physical law than on what we mean by remembering. If memory requires a mind to hold it, then forgetting begins the moment minds disappear. If memory means only that a pattern once existed, then perhaps nothing is ever fully erased, only rearranged beyond recognition. Cosmology can describe entropy and expansion with precision, but it cannot settle which definition of memory is the right one to use. The universe may not forget so much as simply stop being asked to remember. Certain physicists suggest that once no observer remains anywhere, the very question of memory stops making sense, rather than being answered one way or another. A universe with no mind, left to ask what is remembered, has no one to feel the loss, no one to keep score. The concern about being forgotten belongs to us, here, now, capable of imagining an ending we will never witness. Tonight, that capacity is itself something rare and warm, a brief, local miracle of noticing. Rest inside it. Let the vast dark carry on without needing your reply. Good night.